levers keep jamming. Got to get this going soon, get back to the surface. Oh, another interruption. What's your problem up there?
Stella, why are things weightless in space?
Because there's no gravity. It makes you float. It makes you weightless.
Yeah, I know that, but why is there no gravity in space?
It's because there's no air. It's the air pushing down that makes the gravity. Isn't it, Stella?
I'll investigate.
Up in the lab, I set up a mass on a balance in a sealed container. Look at the reading on the balance. This button starts a pump which removes the air from inside the container. Watch what happens to the reading. It goes up. Not what you'd expect at all.
I've got some other surprising effects here. These masses are different sizes, but they have the same weight. The scales balance.
But add some water.
It might look like the weight of one of these masses has changed, but it hasn't. The weight of an object stays the same whether it's in air or water. So what's going on?
Weight is the force of gravity on an object. A force of 10 newtons pulling down on this 1 kilogram mass. But underwater, there's another force acting too. The water pushes up on the 1 kilogram mass with a force called upthrust. So the resultant force pulling down on the spring is less. This upthrust force needs further investigation, and Femi's up to her neck in it already.
Oh, excuse me a moment. Looks like a good strong brew. Absolutely perfect. This investigation starts in this very unusual pool. It's not a swimming pool. In fact, it's impossible to swim here. But it is possible to have a lovely cup of tea.
The water in this pool has a remarkable effect. It's extremely floaty or buoyant. I'm here to investigate why it has such a strange effect.
As I dry off here, look what's left behind. Salt. This pool is filled with very salty water. It's called brine. The brine comes from a nearby underground lake here in Droitwich, which is 10 times saltier than the sea.
I'm not the only one enjoying a float in the brine. Ken here looks pretty relaxed in his tank of brine too. The brine is pushing up with an upthrust force exactly equal to his weight.
But Ken's identical twin brother, Kevin, gets the freshwater treatment. In freshwater, the upthrust is less than Kevin's weight. So he sinks. Sorry, Kevin. So, why is the upthrust in freshwater so much less than the upthrust in brine?
When an object is immersed in water, it pushes some water out of the way. You can see the water level rise in the tank. The object's displaced some water. The same thing happens here. By catching the displaced water as it spills out of the beaker, we can find out exactly how much water Kevin has displaced. The volume of water displaced equals the volume of Kevin. This displaced water is very important. This beaker contains exactly the same amount of brine that Ken displaces when he floats. It's less than his volume because not all of Ken is underwater.
The weight of this displaced brine equals the upthrust force of floating Ken. Watch.
Remember, the reason Ken floats is the upthrust force equals his weight. The force is balance. The upthrust force equals the weight of the displaced brine.
In the fresh water, Kevin displaces this much water, but the fresh water is not as heavy as Kevin. Look.
So the upthrust force in the fresh water is less than his weight, so he sinks. A beaker of brine is heavier than the same volume of fresh water. The effects can be put to very good use. Sylvia Major injured her knee in a car accident. She's been unable to walk for several weeks. For her, the brine pool is a welcome relief. Anne Atkinson is a physiotherapist.
Hi, Sylvia.
Hi, Femi.
Now, you look a lot more at home in here than you did on dry land.
Yes, it's wonderful. For half an hour in here, I can almost forget my injury and I feel really weightless.
Well, Anne, Sylvia's not really weightless, is she?
No, it's just the effect of the salt water, which makes her more buoyant. The upthrust of the water helps to take the weight off her legs and takes the pressure off the injured knee.
While Ken enjoys the upthrust of brine, his cousin Kurt is about to experience the upthrust of air.
It's a much smaller force than the upthrust of water, so you usually don't notice it. But it's enough to send these balloons skywards. The balloons are filled with helium, a gas lighter than air. The upthrust of air pushing up on the balloons is greater than the combined weight of the balloons, the helium, and Kurt. Up he goes.
Upthrust isn't the only force that can make your weight appear to change, as Femi's about to find out when I work out how to rescue poor Kurt.
A weight problem, with a difference. But it's not my problem, it's the bathrooms. I'm travelling in a lift in the tallest building in Europe, the Commerce Bank in Frankfurt. This 50-storey skyscraper has just opened. If I use the stairs, it would take me half an hour to climb to the top floor.
Torsten Lepper, you're the person responsible for these lifts.
Yes, we've installed 18 lifts in this building to save you the climb.
How high are the lifts?
This lift is about 186 meters.
How does it work?
It's pulled up by 9 steel ropes.
Well, I hope they're strong.
Oh yes, extremely strong.
When the lift is at rest, the force of the cables pulling up equals the downwards force of the weight of the lift. To get the lift moving, the lift cables have to pull up with a greater force than the weight of the lift. So what does this have to do with my weight problem?
Could you just help me take that, please, Torsten?
Oh yes,
Thank
see you later.
Bye-bye.
These slippers should help show us what's going on. Stylish? I think so.
As I stand on the springs, they're squashed by the force of my weight pushing down. But there's another force squashing them too, the force of the floor pushing up. When the lift is at rest, the force of the floor pushing up on the springs equals the force of my weight pushing down. The forces balance. But as I start to move up, the lift floor pushes me up with a greater force, so the springs get more squashed.
We're now travelling at a constant speed. The forces balance again.
And as the lift slows down at the top, the floor pushes up less, so the springs are now less squashed than before. And it's not me, but the lift which is making the reading on these bathroom scales change too.
Scales like these actually measure the upward force of the platform on my feet. Usually this is exactly equal to my weight, so there's no problem. But when the lift starts to move up, the readings change. The floor is now pushing up with greater force, so the reading is now bigger than my weight.
The readings on all these scales change too, although none of the weights are really changing. The only way I can change my weight in this lift is by changing my mass, the amount of stuff in me.
And that looks like a tasty way of doing it. Thanks, Dawson.
You're welcome.
Femi got off lightly there. There's another interesting effect you can experience in a lift. Kurt's not going to be quite so lucky.
Let's look at that again. As the lift free falls, look what happens to Kurt. He's floating above the floor. He looks weightless. Of course he's not. But because the lift is falling down at exactly the same speed as Kurt, it produces a weightless effect.
Whatever you do, and whatever it might feel like, gravity stays the same on Earth, so your weight doesn't change.
Yeah, but what causes gravity in the first place? It isn't air, is it?
No, it's something to do with the Earth. It pulls things down.
But what do you mean it pulls things down? What about in Australia? Or the South Pole at the bottom of the Earth?
Yeah, things don't fall off the bottom of the Earth. Gravity doesn't pull things down there, it pulls up.
The force of gravity is caused by the pull of the Earth. It pulls everything towards its center. Gravity acts on everything all the time.
So, is there any situation where your weight really does change? But the force of gravity is different. You can find out. I'm sure Femi can.
My weight didn't really change here. Or here. My mass of 55 kilograms always means a force of gravity of 550 newtons. To find somewhere where my weight really does change, I'm going to have to travel a little bit further.
My first stop on this long journey is the planet Jupiter, an enormous gassy planet. I couldn't really land on Jupiter, but imagine I could. Now, here on Jupiter, my mass is just the same as back on Earth, 55 kilograms. In space, on Earth, on Jupiter, there's still the same amount of stuff in me. So why do I feel so heavy? It's bigger and heavier than Earth. It has a force of gravity too, but the force of gravity is much stronger than on Earth. On Jupiter, my weight is no longer 550 newtons. It's nearly 1,400 newtons. Wow, that's heavy.
The force of gravity on Jupiter is 2.5 times gravity on Earth. Even picking up these bathroom scales is difficult.
And bouncing on my pogo stick is almost impossible. That is until I switch on my turbocharged boosters.
See you later. I've got a long journey ahead. Nearly made it to the most recent planet to be discovered and furthest away from Earth, Pluto. Pluto's even smaller than our moon. My mass is still the same, 55 kilograms. But my weight is only 20 newtons. I weigh the same as a couple of boxes of cornflakes weigh back on Earth. On Pluto, the force of gravity is much, much weaker than on Earth.
Easy, does it? I don't need my turbocharged pogo boosters here. I'm not sure where I am now. Far beyond our solar system, of outer space. And you know what? At last, I've done it. I am totally weightless. There's no force of gravity from any planet because they're all so far away. The only thing is, I'm not sure of my way home. Help!
These coach bolts are too heavy for my cantilevers. What can I do? Strong cup of tea, this'll help me think. Meanwhile, here's one for you. My cup of tea weighs 134 grams. Now, if I put my finger in it, what will happen to the reading?
Nothing. Her finger's attached to her hand.
Yeah, she doesn't add any weight to the cup.
The reading goes up.
It looks heavier. Why?
Her finger's displacing some water, isn't it?
Maybe because the reading's going up by the weight of the displaced water.